Welcome to this deep dive into one of the most fascinating developments in modern condensed matter physics, topological phases of matter. This work earned David Thouless, Duncan Haldane, and Michael Kosterlitz the 2016 Nobel Prize in Physics. Three physicists revolutionized our understanding of matter. David Thouless developed the theory of topological quantum numbers in physical systems. Duncan Haldane discovered how topological concepts can be applied to chains of atoms. And Michael Kosterlitz, working with Thouless, explained phase transitions in two-dimensional materials. Let me start with one of the most shocking experimental discoveries in condensed matter physics, the quantum Hall effect. When this was measured in the early 1980s, physicists were absolutely stunned. Imagine a two-dimensional sheet of electrons confined to move in a plane. We apply a strong magnetic field perpendicular to this plane. When current flows through the sample, a voltage develops perpendicular to both the current and the magnetic field. This is the Hall effect. In classical physics, the Hall resistance increases linearly with the magnetic field. Nothing special, just a smooth, continuous change. But at very low temperatures and strong magnetic fields, something bizarre happens. The Hall resistance doesn't change smoothly. Instead, it forms perfectly flat plateaus. Here's what the data looks like. As you increase the magnetic field, the Hall resistance jumps between perfectly flat plateaus. These plateaus are incredibly stable. The Hall resistance on these plateaus takes quantized values. RH equals h over Ne squared, where h is Planck's constant, E is the electron charge, and N is an integer. Here's what's shocking. This quantization is exact to 1 part in 10 billion. It doesn't matter if your sample is dirty, if it has impurities, if the edges are rough, the value is always exactly h over Ne squared. This raises a profound question. How can a macroscopic property of a messy, disordered material be so incredibly precise? In ordinary materials, properties depend sensitively on details like purity and geometry. Let me contrast this with traditional phase transitions. In conventional physics, we describe phases using local order parameters. Think about ice melting to water. In ice, molecules are arranged in a regular lattice. This regularity is the order parameter. As you heat it up, the order parameter smoothly goes to 0, and you get liquid water. The order parameter is local. You can measure it at each point in space. It describes the microscopic arrangement of atoms or molecules. If you slightly change the temperature or add a small impurity, the order parameter changes smoothly. Everything is continuous and predictable. But topological phases are completely different. They cannot be described by any local order parameter. The distinction is fundamentally global. Topology is the branch of mathematics that studies properties preserved under smooth deformations. You can stretch, bend, or twist, but you cannot tear or glue. A circle and an ellipse are topologically equivalent. You can smoothly deform one into the other without cutting or gluing. They both have genus 0, meaning no holes. But a circle and a donut are topologically different. A donut has one hole, genus 1. You cannot smoothly deform a circle into a donut without tearing it. This difference is topological. Topological properties are characterized by integers called topological invariants. The number of holes in a surface is a topological invariant. You cannot change it by smooth deformations. Thouless, together with Komoto, Nightingale, and Denez, discovered that the quantum Hall plateaus are characterized by a topological invariant called the Chern number. The Chern number n is given by an integral over the Brillouin zone. F of kxky is the Berry curvature, a geometric property of the electronic wavefunctions. This integral always gives you an integer. In the quantum Hall effect, the integer n counts the number of filled Landau levels. Landau levels are the quantized energy levels that electrons occupy in a magnetic field. Here's the key question. Why is this topological invariant so robust to disorder and imperfections? Why doesn't adding impurities change it? The answer is beautiful. Integers cannot change continuously. If n is an integer and you smoothly deform the system, n can only change by jumping from one integer to another. Small perturbations cannot cause such a jump. Adding a small amount of disorder or impurities is a smooth deformation of the Hamiltonian. Since the Chern number is topologically protected, it cannot change unless you close the energy gap. To change the Chern number, you must close the energy gap between occupied and unoccupied states. This requires a genuine phase transition, not just a small perturbation. Let me show you a simple calculation that reveals the quantum nature of conductance. Conductance G is defined as current I divided by voltage V. In classical physics, conductance can take any positive value. But in quantum mechanics, there is a fundamental unit of conductance. G0 equals 2e squared over h. This is called the conductance quantum. Numerically, the conductance quantum is about 7.75 times 10 to the minus 5 Siemens, or about 77.5 microsiemens. This is the conductance of a single perfectly transmitting channel. In a one-dimensional channel, the conductance can only be integer multiples of G0. One channel gives G0, two channels give 2G0, and so on. In the quantum Hall effect, the Hall resistance is h over ne squared. Notice this is 1 over n times h over e squared. The factor of 2 is absent because Hall resistance involves a different geometry. Let me show you a quick calculation of Landau levels to give you intuition for the energy scales involved. The energy of the nth Landau level is h bar omega c times n plus 1/2, where omega c is the cyclotron frequency. The cyclotron frequency, omega c, equals EB over m, where B is the magnetic field strength and m is the electron mass. For a magnetic field of 10 Tesla, the cyclotron frequency is about 1.76 times 10 to the 12 Hertz. This corresponds to an energy spacing of about 7 millielectron volts. This energy spacing of 7 millielectron volts is much larger than thermal energy kBT at low temperatures. At 1 Kelvin, kBT is only about 0.086 millielectron volts. This is why you need low temperatures, to see the quantum Hall effect. One of the most remarkable predictions of topological theory is the existence of edge states. These are conducting channels that exist only at the boundary of the sample. In a quantum Hall system, the bulk is insulating, but the edges are conducting. Current flows only along the edges. These edge states are topologically protected and cannot be scattered backward. This is called bulk boundary correspondence. The number of edge channels equals the Chern number of the bulk. A topological invariant of the bulk determines the number of conducting edge modes. The edge states are chiral, meaning they propagate in only one direction. On the top edge, electrons move to the right. On the bottom edge, they move to the left. There is no backscattering. This explains the perfect quantization of the Hall conductance. Since there is no backscattering, the transmission is perfect. The conductance is exactly n times e squared over h, with no corrections. Now let's address a subtle but crucial point. Disorder actually helps stabilize the quantum Hall effect. This seems paradoxical. How can adding impurities and defects make the system more stable? Shouldn't disorder destroy quantum effects? Disorder localizes states in the gaps between Landau levels. These localized states do not contribute to transport. They trap electrons and prevent them from conducting. As you add disorder, the localized states fill more of the energy gap. This actually widens the plateaus in the Hall resistance. The quantization becomes more robust. The extended states that carry current remain at the centers of the Landau levels. As long as the Fermi energy is in the gap, you get perfect quantization, regardless of the amount of disorder. Let me now discuss a different type of topological transition discovered by Kosterlitz and Thouless in two-dimensional systems. In 2 dimensions, thermal fluctuations are strong enough to destroy conventional long-range order. You cannot have a ferromagnet or a crystal with true long-range order in 2D at finite temperature. However, you can have topological order mediated by vortices. These are point-like defects where the phase of an order parameter wins by 2 pi as you go around them. Here's a vortex. As you go around the center, the phase or the direction of some order parameter rotates by 360 degrees. The center is a topological defect. Vortices are characterized by an integer winding number. If the phase winds by 2 pi, the vortex has charge plus 1. If it winds by minus 2 pi, the charge is minus 1. At low temperature, vortices and antivortices bind into pairs. These pairs have zero net topological charge and do not destroy order. The system behaves like a superfluid or superconductor. But above a critical temperature, the Kosterlitz-Thouless temperature, the pairs unbind. Free vortices proliferate and destroy the topological order. The system becomes normal. The Kosterlitz-Thouless temperature is proportional to the superfluid stiffness ρs divided by Kb. This transition is continuous, but has no local order parameter. It is purely topological. The ideas of Thouless and collaborators have blossomed into a vast field studying topological insulators and topological superconductors. Unlike the quantum Hall effect, which requires a magnetic field, topological insulators can exist even when time reversal symmetry is preserved. They have insulating bulk, but conducting surface states. A three-dimensional topological insulator has an insulating interior but metallic surface states. These surface states are protected by time reversal symmetry and topology. Topological insulators require strong spin-orbit coupling. This couples the electron's spin to its momentum and leads to non-trivial band topology. The spin-orbit coupling Hamiltonian is lambda times sigma dot p cross grad v, where sigma is the vector of Pauli matrices, p is momentum, and v is the potential. This term mixes spin and orbital degrees of freedom. Time reversal invariant topological insulators are classified by a Z2 topological invariant. This is either 0 or 1, telling you whether the system is topologically trivial or non-trivial. Let me discuss some key experimental systems where these ideas have been tested. Bismuth selenide and bismuth telluride are prototypical three-dimensional topological insulators. They have strong spin-orbit coupling and a single Dirac cone on each surface. These materials have been studied extensively using angle-resolved photoemission spectroscopy, or ARPES. This technique directly images the electronic band structure. Scanning tunneling microscopy can image the surface states and show that they are robust against impurities. You can see electrons scatter around defects, but the surface states remain conducting. A remarkable achievement is the quantum anomalous Hall effect in magnetically doped topological insulators. By adding magnetic dopants like chromium or vanadium to a topological insulator, you can break time reversal symmetry. This opens a gap in the surface states. The result is quantized Hall conductance without any external magnetic field. The magnetization of the material itself provides the necessary symmetry breaking. This was observed in 2013. One of the most exciting applications of topological phases is for quantum computation using Majorana fermions. Majorana fermions are exotic particles that are their own antiparticles. They can emerge as zero-energy bound states in topological superconductors. Quantum information stored in Majorana states is topologically protected. Local noise cannot destroy the information because the Majorana modes are spatially separated. By moving Majorana fermions around each other, a process called braiding, you can perform quantum logic gates. The result depends only on the topology of the world lines, not the detailed path. Majorana fermions have been searched for in hybrid systems combining superconductors and semiconducting nanowires with strong spin-orbit coupling. Evidence includes zero-bias conductance peaks. The discovery of topological phases has transformed condensed matter physics and opened connections to many other fields. Topological phases have created deep connections between physics and pure mathematics, including differential geometry, algebraic topology, and K-theory. There is now a periodic table of topological insulators and superconductors classified by symmetry and spatial dimension. This classification uses sophisticated mathematical tools. The ideas have spread beyond electronic systems to photonic crystals, acoustic metamaterials, and even mechanical systems. Topological protection is a universal concept. Let me give you a sense of just how precise the quantum Hall effect is. The von Klitzing constant h over e squared equals 25,812.807 ohms. This is known to extraordinary precision. The quantum Hall effect is now used to maintain the international standard for electrical resistance. It is more precise than any artifact standard. The relative uncertainty is less than 1 part in a billion. Even if you change the sample geometry, add impurities, or vary the temperature slightly, the value remains exactly the same. This incredible precision is a direct consequence of topology. The quantization is protected by the integer Chern number, which cannot change under smooth deformations. Let me summarize the key concepts we've covered in this lecture. Topological invariants are integer-valued quantities that characterize global properties of a system. They cannot change under smooth deformations. Topological phases are incredibly robust to disorder and imperfections. Small perturbations cannot change the topological invariant. The bulk boundary correspondence states that topological properties of the bulk determine the existence and number of edge or surface states. Physical responses like conductance take quantized values with no corrections from interactions or disorder. This is unique to topological phases. Topological order is fundamentally different from conventional order described by local order parameters. It is a global property. Despite tremendous progress, many questions remain open. Most topological effects require low temperatures. Finding materials with large gaps that work at room temperature would enable practical applications. Most theories assume non-interacting or weakly interacting particles. Understanding strongly correlated topological phases is a major challenge. Building a functional quantum computer using Majorana fermions requires overcoming significant experimental challenges, but the potential payoff is enormous. Recent work has extended topological ideas to semimetals, wave fermions, and even higher-order topological phases. The field continues to expand. The 2016 Nobel Prize recognized work that began in the 1970s and 80s. It took decades for the full impact to be appreciated. David Thouless showed how topological concepts from mathematics could explain physical phenomena like the quantum Hall effect. He introduced the TKNN invariant. Kosterlitz and Thouless discovered a new type of phase transition mediated by topological defects. This applies to superfluids, superconductors, and many other systems. Duncan Haldane showed that topological phases could exist without external magnetic fields. He discovered topological properties in one-dimensional spin chains. The work of these three physicists has created an entire field of research. Thousands of scientists now work on topological materials and their applications. Topological phases of matter represent a fundamental shift in how we think about the organization of matter. The appearance of integers in physical measurements is profound. It tells us that nature cares about global topological properties, not just local details. The extraordinary precision of topological quantization arises from mathematical necessity, from the fact that integers cannot vary continuously. This is physics at its most beautiful. Deep mathematics, precise experiments, and fundamental insights into the nature of matter all coming together. Thank you for joining me on this journey through topological phases of matter. The work of Thouless, Kosterlitz, and Haldane has given us a new lens through which to view the quantum world.